Hi, in this screencast what I'm going to do is show you how to model the motion of a fan cart that has the fan turned on, so it's experiencing a constant force. What we're going to start with is a piece of VPython code that already models the motion of a fan cart moving with constant velocity. So the first thing I'm going to do is talk through these elements of the code that model the motion, and I'll show you what it does. So starting at the top, we have two lines of code that import some important modules that we need to do the modeling in VPython. Below that, we have two lines of code that actually set the size of this window so that you can see it on screen. So I'm going to add a little comment here that tells me that that sets up the windows. You don't always have to do this, but it's kind of useful sometimes if you're trying to see something. The rest of the code we're actually going to talk about and talk about the structure of it. So the next two lines of code actually set up the two objects that you see. And it's often the case that we have objects in our code. So the first is a track, which is this long gray bar. It has a position vector, which is centered at 0, and then it has a size. It's 10 meters long and so forth. The fan cart is this red block, and it has a position vector that starts at minus 4.75 meters. The reason for that is it starts on the end of the track, as you'll see in a minute, and it has a particular size as well. So these objects are meant to represent the track and the fan cart that we would have in the laboratory. The next lines of code actually set up the parameter values that we need to model the motion. So the fan cart has a mass of 0.3 kilograms, the fan cart has a momentum of 0.15 kilogram meters per second, and so forth. So these parameters are actually used to set up the situation that we're modeling, a particular fan cart with a particular momentum. The next two parameters set up the time. They tell us we start the clock at 0 seconds, and every time we're going to iterate, we're going to go through the loop calculations. We're going to do that every half a second. So this is the time and the time step, and it turns out that these are really important bits, especially the time step, as you'll find in future work. The last thing here is the calculation loop, which in VPython is usually a while loop with a colon to separate the contents, the stuff that's inside of the while loop that gets calculated every time it executes, from the rest of the program. So this is the calculation loop. And what we're doing is we're going to model the motion for 10 seconds. In that motion modeling, we are updating the position of the fan cart. So here's the new position. It's equal to the old position plus the average velocity times the time step. So this is how you actually write the position update formula in VPython. After we do that calculation, we update the time so that when we get into the loop, we start out with 0, we go to 0.5 seconds, then 1 second, then 1.5, and so forth until we get to 10. Once we get to 10, we leave the loop. This rate statement slows down the calculations so that we can actually see it on screen. So I'll go ahead and run this piece of code right now, and you'll see the fan cart moves to the right. It looks like it moves at constant velocity, but there's a way that we can actually visualize that. So we're going to create a new object. We're going to call it fan cart motion map. It's a motion map object, and it's a series of arrows that represent quantities that we are interested in. So the motion map object will take as its input parameters the object that you care about. So in this case, we're talking about the fan cart. We want a motion map of the fan cart. The final time that you want to calculate, or that you want to represent the motion map for, so that's about 10 seconds. And let's say we'll do 10 markers. So we're going to get 10 arrows. And that's it. That's all we need to set up a basic motion map. However, if we were to run the code, we wouldn't see anything. Because what we have to do is we have to tell the motion map object what thing are we going to pay attention to, what quantity do we want the arrows to represent. So in the calculation loop, we're going to add one bit of code. So we will update the motion map with the time, what time it is, so that it knows when to put down the arrow, and the quantity that we care about. In this case, we're going to follow the fan cart's momentum vector. Now, a motion map has to have a vector here, so that's why I have the full fan cart momentum. Now, if we run the module now, what you'll see is little arrows that show up to represent the fan cart's momentum. Notice that they're all the same size and they're equally spaced. So that gives us some information that this fan cart is moving at constant velocity or with constant momentum. And that makes sense because we have no force acting on it. We haven't programmed a force in. The other thing you'll notice is that there are numbers which represent each of the arrows, and that's to help you sort of know what order that they come in, so that if something goes to the right and then goes to the left, you know what the arrows are following. So one thing I do notice is that these arrows are quite small. So what we're going to do is we're going to actually add another parameter here. It's called marker scale. And what it is it's a multiplicative factor that makes the arrows twice or 3 or 4 times as long. In this case, I'm going to make them twice as long so I can see them a little better. So now I can see them quite a bit better. Alright, the last thing to do is to make the fan cart move under constant force. So there's a fan that pushes, there's air that pushes on the fan as the fan pushes air back to move the cart to the right. It accelerates or it changes its momentum at a constant rate. So we're going to add that fan force, and we're going to say that it's roughly 0.025 newtons. And that it points to the right. Oops, I forgot to add that it is a vector. That actually doesn't matter. VPython will understand that, but I wanted to make sure I was explicit about it. Now, just putting that force in there doesn't do anything. If we run the module again, we'll see we get the exact same motion, because we haven't actually used the momentum principle to update the momentum based on the force. So we'll type fancart.p, the new one gets the old one, so it's equal to the old one, plus the impulse, which is the force of the fan times delta t. So this is the momentum principle in its update form written for VPython code. Now if we run that, what you'll see is the cart accelerates to the right, the spacing between each arrow gets larger and larger as you move to the right, and the arrows themselves get longer and actually bigger because of the way that VPython does the scaling as they move to the right. So this is a fan cart that is moving to the right under the constant force of a fan. One other thing to do is actually we can track the fan force instead of the momentum. We can change the fan cart's motion map to represent the force of the fan at every point to make sure that it's constant throughout the motion. So we do that, and you'll probably not see it. You'll see little dots. So we have to turn the scaling up to maybe, I don't know, let's try 20 for now. See if you can see them now. And those will be all the same size, but notice that their separation is greater and greater as you move along. That's representing the accelerated motion, where the arrows are representing the force, which is constant. Let me turn that back to the momentum vector. So we leave with the idea that for constant force motion, what you have is an object which changes its position in increasing amounts all the way along, and that its momentum vector gets longer, or velocity vector for that matter, gets longer as it moves along as well.